Water is a particular passion of mine, trying to demystify it for people. I really consider water to be that final frontier, the one that can take your beers from being good to being great. Once you understand how water works, how water chemistry works, and you can start taking into account, and there's some chemistry, but it really is a big picture kind of thing. Once you understand the ballpark, you can start considering it, taking into account in your brewing, and your beers will really improve. Beer pH. It's like tuning the radio dial. You're trying to get that station to come in nice and clear. Same thing with your beer. When you get the pH of the beer right, you better express the flavors of the beer to your palate. The example I always use is spaghetti sauce. You can buy spaghetti sauce in the jar, and it's very bland. And you make bland spaghetti. You go to a restaurant, or somebody that says, "Oh, this is very fresh, homemade from scratch," and it's the most acidic spaghetti sauce you've ever had. It's etching your teeth. Of course, it's very bright and tomatoey, but that's about all you can taste. So, in between there is that sweet spot is the right pH where you get some acidity, you get a rich tomato flavor, and you get all the herbs and spices that are in that sauce being expressed. It's not bland, it's not too sharp, it's just right. And the same thing with beer. When you get the beer pH right, that's when the beer tastes the best. And the beer pH is directly affected by your mash pH. And your mash pH is directly affected by your water and your grain bill. The beer pH, which best expresses the beer's flavors, is driven by the mash pH, and that's driven by the water chemistry and the grain bill. And whenever you're talking about brewing and brewing chemistry and water chemistry, it's very easy to get wrapped up in what you think the rules are or calculations say. And this is it's not a perfect science. I mean, there's a lot of art in brewing. And one thing that I want to emphasize is whenever I'm talking about, these relationships, there are rules which are meant to enforce the guidelines, which are derived from the principles that suffice until you really understand what you're doing. And so we're going to lay out some rules, we're going to lay out some guidelines, but within that you've just got to brew and experience it and play with it until you develop that understanding and that feel for the results. And that will be your best guide. So a lot of good brewing software out there. Beersmith, ProMash, Beer Tools. There's a lot of good software that will help you. I have a spreadsheet that I have on my website, howtobrew.com, in section 3, chapter 15, that will help you with water. But again, it's just a tool, and you can be led astray by the calculations in that spreadsheet. They may tell you need an alkalinity of 400 to brew this Russian Imperial Stout. You don't need to go that high, but that's because it is a literal calculation. It's a very linear calculation, and brewing, being a natural science, is not strictly linear. So that's one of my final caveats is don't always pay strict attention to the rules. Get the big picture, and use your experience and judgment to produce the best beer. Why water matters? Well, like I said, it's the final frontier. It's the 10% that'll take your beer from being good to being great. And the players in water chemistry are your brewing salts. Calcium, magnesium, and alkalinity affect the pH. That's how you express your flavors. Sulfate, chloride, and sodium, to some extent, are your flavor ions. The sulfate accentuates hop bitterness, chloride accentuates the malt character, and your sulfate to chloride ratio kind of determines, is that beer going to be malt forward or is it going to be hop forward? So if the sulfite chloride ratio is 1 to 2, that means the malt character is dominant, and you're going to get a nice, round, soft, rich malt character out of that beer. And notice we're talking ratios, not 50 parts per million to 100 parts per million necessarily. It can be 10 to 20 or 40 to 80, but it's a ratio. And likewise, if the sulfate to chloride is 2 to 1, hop bitterness is dominant. And that's good for IPAs. In fact, for IPAs, Colin Kaminsky of Downtown Joe's in Napa, he's done a lot of work with the sulfate to chloride ratio. And he's found that on a really clean IPA, he can go up to 9 to 1 without that beer tasting minerally. And that's one thing you've got to watch when you're adjusting your water with brewing salts, is that you don't produce mineral water and mineral beer. I've had some like that, and they're just, they're not as good as they could have been. You do get that sensation of drinking mineral water in the background of the beer. So you don't want to go overboard. I would say in terms of total sulfate on a 9-to-1 ratio, you don't want to be over 300 to 400 parts per million of sulfate. This is another kind of point that I'm not sure, I think I get to it later in the talk, but just because Burton-on-Trent says they've got hardness at 300 and sulfate at 500 and so on, and that's where this Bass Ale came out of, or the hoppy style came out of. Those brewers didn't like brewing with that water. As brewers, we've been changing our brewing water for the last 300 years at least, if not longer. So don't get stuck on trying to emulate a particular brewing city. You're often going to be doing too much. So one thing, and so later in talk, one thing I'll talk about is, you can use that as a guide, as a potential goal or target, but you got to understand on when you're close enough and just to leave it alone. So anyway, when adding salts for RA or residual alkalinity or pH adjustment, calcium chloride is good for your maltier styles. Calcium sulfate is good for your hoppier styles. That's because you're changing that chloride to, sulfate to chloride ratio with those salts. That brings up a great point. Whenever you're monkeying with your water, you need to have a water report so you know what you're starting with. Here in Minneapolis, the water's pretty soft, what we call soft. It's surface water. It doesn't have a whole lot of dissolved mineral in it. If you go further north or further west, you get into groundwater sources, limestone aquifers. Then you can have very alkaline, very hard waters. Hard water, by definition, contains high amounts of calcium and magnesium, and also iron and manganese and other metals. Those are your cations. Hard water can range from the pH can range from 5 to 10. Hard water is good for brewing. So often you get used to hearing, this water that we're brewing with, it's very hard, so I have to change it. It's too, and actually hard water is good for brewing. It's the metal ions that you want. It's the alkalinity that you don't want. The bottom line when looking at water for hardness is you're looking for calcium levels in the at least 50 parts per million. 100 parts per million is great. 200 is probably a little too high, and anything over 200 is probably way too high. But at least 50. And I today when we brewed the oaked mild, we ended up with we did some calcium additions and ended up with a calcium concentration of 80 parts per million for that beer. Soft water does not contain high amounts of calcium and magnesium or other cations. Pilsen, Portland, places where you have surface water or melt water sources, you don't have the dissolved minerals. And the pH, the pH of soft water can be 7 to 10. You're probably not going to get down to the 5s. Lower pHs are driven by the water hardness, but the water can still be low in hardness and high in alkalinity. When it's high in alkalinity, that's when you go above 7 to 10 pH. And here's a very important take home. Soft water can be alkaline, but alkaline water is not necessarily soft. So if you see a water report that says the water pH is 8, it tells you really nothing about the levels of hardness and alkalinity in the water. All that 8 tells you is that balance. You can have a pH 8 water that is very soft, or it can be very hard, depending. What does water pH mean? You look at your water test report and you see pH 8.5 or 8 or 9. What does it mean? not much. And I like this picture because you see the little girl and the big guy on the end of the teeter-totter. The little girl is alkalinity. Alkalinity dominates your water chemistry. You know, you can have water that is just coming out of the tap. You think, you know, you see some scale, you see on the pipes, or you know, you taste it and it tastes minerally, and you think, well, this is hard water, I need to soften it. Well, you soften it, you take out what existing hardness there is there, but you leave all the alkalinity behind. And it's the alkalinity that you're always struggling against when you're brewing, because that's what's going to pull your mash pH higher than it needs to be, or that you want it to be. So what does water softening do? Well, salt-based water softeners exchange sodium ions for the calcium and magnesium. So, as I say, you're throwing the baby out with the bathwater. You want the calcium in your brew, and you don't want the alkalinity, but typical water softening leaves all that alkalinity there and just takes away the calcium you need. Mash pH, this is one thing that how to brew may not have been made terribly clear. You're looking for a consistent mash pH, whatever style of beer you're brewing. It should be 5.4 to 5.8 when you measure it at room temperature. That is, letting that wort sample cool down from the mash temperature to room temperature, testing it with a little pH strip or a handheld pH meter. If it's at room temp, you're looking for 5.4 to 5.8. If you're at mash temp, the difference in temperature creates a difference in chemical activity, which causes the pH to be higher or lower, 5.1 to 5.5. When we say higher chemical activity, the pH scale is actually the anti-log of the hydrogen ion concentration. So it's a lower number, but yet higher activity of hydrogen. So that's the temperature effect, a difference of 0.3 pH units according to temperature. The pH test papers are made to be used at room temperature. That's where they're calibrated at. They're indicators, the indicators that are in the test paper are made to work at room temp, 70 degrees or so. Calibration solutions, same way. When you calibrate your pH meter, those are made to work at 70. If you get the temperature correction factors from the manufacturers, you can see that like at mash temperatures, you're off by half a pH unit or more. pH meters with ATC, or active temperature compensation, they give the actual pH at the measurement temperature. And so if you have a pH meter that has ATC in it, temperature compensation, you can stick that in the mash. It's not terribly good for the probe, but some of them are designed to take that use in the temperature. And so you're measuring at temp, then you're looking for the 5.1 to 5.5 range. If you allow that to cool down to like 100 or 120, then you got to kind of think, well, maybe halfway between room temp and mash temperature. And so I'm looking at somewhere in between that 0.3 difference, whatever that is. I don't have a good conversion curve for that. Nobody's published data on what those numbers should be at different temperatures. We just know that at room temp, 5.4 to 5.8, mash temp, 5.1 to 5.5. So pick one or the other. What is alkalinity? If you look in the upper left, you see the CO2 is coming from the atmosphere. As carbon dioxide dissolves into water, you get what we call aqueous CO2 there on the left. And as a certain percentage of that will convert from aqueous CO2, that is CO2 that is associated with water atoms, to being actually hydrated. And when it's actually hydrated, that's when you form carbonic acid, H2CO3. And even there, that carbonic acid is a very small percentage, like 2% or less. So when we talk about carbonic acid, we're really talking about this situation of hydrated carbon dioxide and a small percentage of carbonic acid. Just for clarity, I don't know. It doesn't make a whole lot of difference to this talk. Anyway, so a carbonate comes from carbon dioxide in the atmosphere. It also comes from the ground where you have calcium carbonate or dolomite or any of other calcium carbonate bearing minerals that dissolve. And there you get the calcium ion coming off when you go in the water, and you get carbonate, CO3, or is it 2? Should be 3. Anyway, CO3 minus 2. And you have 3 forms that carbonate exists in water. You have the carbonate, the bicarbonate, and the aqueous carbon dioxide, carbonic acid forms. 3 forms that it exists in. Next slide will show us the relative percentages. Depending on the pH of the solution or the water, let's say we're here at 8.3, which is a fairly typical drinking water kind of pH. What this chart says is that 98% of the carbonate species in equilibrium at pH 8.3 is the bicarbonate, HCO3 minus 1. If we're at a higher pH, like 12, then this becomes a very low percentage, and the carbonate is the highest percentage of the 3 forms. Over here, when we get into the mash, and this gray bar is the mash pH range, again, bicarbonate, HCO3, goes away, and most of it transforms to the aqueous carbon dioxide form. The kicker is that these reactions occur very slowly. So if you add high alkalinity water to the mash, it's not going to instantly transform from carbonate to bicarbonate to carbonic acid. It's going to be a very slow transition over several hours, if not days. That's one reason when you do calcium carbonate additions to your mash, chalk additions, that it doesn't go into solution very well, it doesn't dissolve very well, and you don't see the mash pH response from calcium carbonate additions that you would expect from the spreadsheets and the brewing softwares, because even though that's what happens, it happens slowly. So I throw that out there, and I'm sure I've confused several people, but just be aware of that background info. The mash is a weak acid, weak base situation. So the reactions occur slowly. Unfortunately, I don't have good data or information on exactly how slow or what that rate is. It's just that, you look at, I've talked to water chemistry professors that say, oh yes, this should happen, that this is the equilibrium, form, this should happen. And then I talked to notable brewing scientists like Charlie Bamforth that have the experience of knowing this info, and then testing and seeing it occur in the mash and knowing what's going on, and say, yeah, it doesn't happen that fast. You add it, and the math says that you should get 2 equivalents of hydrogen ions from this addition, and yet when you measure the response, the pH response of an addition, you only see 1 equivalent worth. So I think, in other words, you add calcium carbonate to the mash, the calcium comes off, you've got the carbonate that should be +2, but you only seem to get +1 activity out of it. Kai Troister's done some nice experimental work in the last couple of years where he did a bunch of titrations with different additions and different chemistries in the mash, in actual mashes, test mashes, and that was what he observed. And it makes sense from my own brewing experience and my own trials and so on, experiments I've run, but it doesn't really jibe with what the water chemistry books say. They say it should be instantaneous, but it seems to be, the kinetics seem to be much slower. Beer and mash and beer pH is the net effect of the hardness, the alkalinity, and the grain bill. The grain bill having some natural acidity that helps, is a player in this game. Here's where we talk about residual alkalinity. This is alkalinity that remains after you've started the mash. Certain equations have occurred, and I'll show you those. And you're with the calcium and magnesium in the water, and you're left with what we call residual alkalinity. The equation for that is residual alkalinity equals alkalinity, that is the total alkalinity as calcium carbonate that you see on your water report, minus the calcium hardness divided by 3.5, plus the magnesium hardness divided by 7. The unit for this equation is milliequivalents per liter, which is not the same as parts per million. Parts per million is raw concentration. Milliequivalents per liter is parts per million divided by the activity, the equivalents, number of equivalents in that atom or molecule, as the case may be. So that's why you have the little factors underneath there. The magnesium is half as effective at pH change as calcium is. High residual alkalinity means that this water that you're brewing with has a higher pH, more alkalinity than hardness, and it's going to pull that mash pH towards 6. To counteract that, you brew a darker beer, one with more intrinsic acidity because of the dark grains. So high residual alkalinity means you brew dark beers. Low residual alkalinity means that you brew light beers. I talk about this as balancing a triangle. Pick any triangle, you've got some amount of water alkalinity, some amount of water hardness, and you've got some grain bill. And where those values balance is going to be your mash pH. And what you want, and that mash pH may be 4.9, it may be 5.8, it may be 5.3. You want it to be in the 5.3 range and not higher or lower. This is the equation generated by my friend A.J. DeLange, but it diagrams that equation you see there across the top. There's at least one form of it where the calcium and magnesium combine with the malt phosphates and carbonates to generate calcium phosphate and carbon dioxide and water and 2 moles of hydrogen ions. And that is what drives so you take, you have your water at pH 8, you have your grain bill, you put them together and create the mash, and then you're looking at a mash pH of 5.5. That it's those 2 moles of hydrogen atoms over there on the right that is causing that pH drop. That's where this is coming from. The calcium reacts with the malt phosphates to generate a precipitate, carbon dioxide, water, and 2 moles of hydrogen ions. Woohoo! The relationship between tannin extraction from dark grains, high pH does it. When your mash pH gets above 5.8 to 6, 6.2, somewhere in there, that's when you start pulling out the tannins and the silicates from the grain husks. You can counteract that by reducing the temperature. If you instead of being at 150, you drop that down to 100 or 120. You've also dropped the extraction activity of that water. So your pH could still be 6, but by dropping the temperature, you've decreased how much of the tannin you're getting out. So yes, that's why when you have very soft water and you want to brew a dark beer like this, you can do cold extraction of your dark malts and then just add that wort to your boil and not really go through the higher temperature mash to reduce that impact. All right, well, this is the fun stuff. Back in 2007, I think it was, I did when NHC was in Denver, I did a really neat experiment with a couple of guys where I just gave directions by long distance and they did all the work. And we made 2 waters. We made a high residual alkalinity water and a low residual alkalinity water. And We brewed 2 recipes with the right water and then brewed the same 2 recipes with the wrong water and compared the beers. So there you can see the residual alkalinity values. One was -50, which is a very high hardness, low alkalinity, kind of residual alkalinity. And that's intended for pale beers, as I said. Higher than the 200 residual alkalinity, that's intended for the dark beers, and we brewed the stout both ways. The end result when we tasted the beers was that the beers brewed with the wrong residual alkalinity water had a more one-dimensional flavor to them. The ones that were brewed with the right RA water for that style had a lot more complexity. You could pick out different flavors. Here's the pale ale recipe. Nothing too fancy. 2-row Vienna, some Carapils, Caramel 40, a couple of hop additions, and 41 IBUs, 1050, California ale yeast. Just a pale ale. The next slide is the stout recipe, I think. This was a foreign extra stout, and it had a lot of dark chocolate, black malt, special roast, crystal lady, roast barley. Pretty dark beer. The color calculates out to 45 SRM using the Mori equation. Again, about the same OG, 1050, and about the same degree of bitterness as the pale ale. This was about 45 versus 41, but really that's pretty ballpark in terms of bitterness. And I wanted to keep those numbers near so that we weren't judging apples and oranges when it came time to tasting the beers and comparing them. So the pale ale, over on the left, you see the pale ale with the residual alkalinity of -50. 1046, final gravity 10.9, apparent attenuation 80%. Mash pH was 5.5, right where we wanted it. Beer pH was 4.5. Okay, we go over to the pale ale brewed with a high alkalinity water, which should be an RA of 200 is pretty typical for people that are brewing with groundwater. It's not that high in RA, and you see the mash pH went from 5.5 to 6.1. Beer pH went 4.5 to 4.7. Again, the fermentation has the yeast have a great deal of buffering effect in driving that pH down to mid 4s or low 4s in most beers. But the difference between these two beers is only 0.2 pH units. Yet when we were tasting the beers in the room, we tasted the high alkalinity beer first, and everybody said, "Oh yeah, this tastes like a good hoppy, bitter pale ale." And I said, "Okay, now try the second one." And I said, "What do you taste different?" And everybody agreed that the second beer you could differentiate between the malt flavors and the hop flavors. There was where the first beer was one-dimensional, the second beer had complexity. You could differentiate the two characters in it. So just a very small pH difference made a big difference in taste. Again, mash pH 5.4, beer pH 4.6. You brew it with the wrong water, you had a much lower pH, 4.9, and a beer pH of 4.2. A little more difference there in the final beer pH. Most water reports are the annual averages for the particular mineral. So you look at the calcium number for the year. That could depending on the changes of the water source during the year. So maybe during the summer they pull from the lakes, during the winter they pull from wells, or vice versa. That can have a significant effect on the chemistry of that water. And so when you're looking at say classic brewing studies on the web, you say, "Oh, here's the water analysis for Dortmund," or "Here's the water analysis for Munich," or one of the classic brewing cities. You got to understand that that's probably an annual average, and it may have occurred from 5 different wells in the area, or a winter to summer source water variation. Use it as a guide. use it maybe as a, just a kind of as a big picture, but don't try to match it, because it's a very poor target to base your beer from, because you don't really know what the real brewing water was when they developed the style. So when you're trying to design a water for a recipe, you're going to brew a brown ale, let's say. Don't get stuck on trying to match a particular brewing city's water. Instead, say to yourself, I'm going to brew a brown ale. That means that the color is 20, 25, and that has some acidity to that grain bill. So to balance that acidity in that grain bill, I'm going to want a brewing water with a little higher residual alkalinity than I may have. Let's say we're here in Minneapolis. Minneapolis being low RA water, you may want to bump up the alkalinity of the water, for brown ale that you're brewing here. You would do that by adding calcium carbonate or sodium bicarbonate to get the alkalinity up a little bit. Match the residual alkalinity to the color of the beer style. That's your first guide, and it really is a guide. You want to ballpark this stuff. Your second consideration is going to be the chloride to sulfate ratio. Do you want that beer to be malt forward, or do you want it to be hop forward? So when you're adding calcium or magnesium sulfate or calcium carbonate, or whatever salt you're adding, look at the result of that salt addition and say, am I increasing the chloride too much? Am I getting a 2-to-1 chloride to sulfate ratio for this IPA? Well, that's not what I want. I want the sulfate to chloride. I want the sulfate to be higher for a hoppy beer. In my ongoing passion for understanding water, Brewer's Publications they said we need to have a malts book, a hops book, water book, yeast book. Yeast book is out there. Hops book is coming. The water book was supposed to be ready for this fall, and I worked hard all last fall and visited Sierra Nevada and New Belgium and a couple other breweries, trying to assemble lots of source material. And my co-author and I realized that we just didn't know enough about what we wanted to talk about. As soon as you start digging at water, it gets really complex, and half of our struggle is trying to figure out how much chemistry do we present to the average brewer. Brewer's Publications, of course, wants a book that can cover any brewer, both the advanced home brewer as well as a professional brewer. So professional brewers, they may have more restrictions when it comes to changing their water to accommodate a particular recipe, but they've also got more considerations on water treatment after brewing, whereas the home brewer doesn't, they just dump whatever they don't need. And some of the larger breweries, Stone, Sierra Nevada, they've got to treat all of the water that they release. They can't have water with high biological oxygen demand or chemical oxygen demand going to the sewer and to the city water treatment plant, because they get fined for that. It's too much treatment load. So what Colin and I have been doing is researching these different water treatment methods, different source water treatment methods as well, so we can put together a comprehensive book. In fact, the title for it is going to be Water, a Comprehensive Guide for Brewers. And it's a guide. And, we quickly realized that we couldn't be the last word in water chemistry. It's much too complex. There's way too much stuff to cover. But what we can do is cover A to Z, in terms of a snapshot or over an overall picture. Here are your options if you're trying to do source water treatment. Here are your options and the relationships if you're trying to do recipe water adjustment. Here are your options for wastewater treatment, and that's where the book is going, and we're still working on it. Thank you all for coming. I really appreciate the opportunity to talk to you all.
Thank you, John. Appreciate it.
Thanks.